So, welcome back, students. Now, till now, whatever we have learned in statistical mechanics, so we have learned about the phase space. Okay, we've learned about the what is the macro states and micro states. Okay, and then we have come to the three statistics, that is Maxwell's Boltzmann, and then we have learned the postulates of Maxwell-Boltzmann statistics. Maxwell-Boltzmann particles are distinguishable. They are spinless particles. They do not obey Pauli exclusion principle. Then there are Bose-Einstein statistics, and then there are the Fermi-Dirac statistics. And we have arranged the particles in the various energy states, obeying that. Okay. Now further moving, we'll see that there are one more important term here left, that is most probable distribution function. Okay, most probable distribution function, most probable distribution function for MB, BE and FD. Okay, most probable distribution function for MB, BE and FD statistics. Okay, now you can add this point also. Actually, in question, a big question of 6 or 7 marks can come about, do a comparative discussion about the MB, Bose-Einstein and FD statistics. There also you can add this. Now, what is this distribution function? Why do we need this actually? Okay, now I think you are very well accustomed to this term distribution function in class 11-12, because you have already studied the kinetic theory of gases, where you have studied the most probable velocity distribution, which is something like this. Most probable velocity distribution function, that is something that was FV, something FV versus V. Most probable velocity distribution. Okay, so we have already studied this. So in statistical mechanics, as I have told you, that already it basically deals with the most probable thing. Everything it deals with the most probable thing only. That only describes the entire motion of the system. Okay, your main concern is to find the most probable distribution, or which most of the particles will follow. Okay, now so for example, the very easy example in everyday life is, suppose you go to a marriage party of your relative. Okay, now in the marriage party there are various stalls. Okay, somewhere there is the rice stall, somewhere there is a chapati stall, somewhere there is a stall of chicken, somewhere there is a stall of veg, somewhere there is a stall of sweets. Okay, now there are many people there. Maybe 1,000 people are they are invited there. Okay, now all will not eat rice, or all will not eat chapati, or all will not eat sweets. Okay, certain people will eat rice, certain amount of people will eat sweet, like that. So now you keep certain people in the stall for rice. One people, that is the people who serve, the caterer. Okay, one people in the rice stall, one people in the chapati stall, one people in the sweet stall, one people in the chicken stall, one people in the mutton stall. And after the marriage party ends, you tell them that, okay, give me a data of the things, that how many people have eaten this, how many people have eaten that. So there, what will you get? You will get a distribution. that okay, 50 people have eaten rice, 100 people have eaten chapati, 40 people have eaten the sweet, 150 people have eaten chicken. So in this way, you will prepare a distribution. Actually, a distribution is there. Okay, a distribution, and whenever the number concerned is very much, very high, then actually you talk in terms of this distribution. Okay, then you talk in terms of this distribution. So for these statistics also, you have to find out this distribution. Now here also the number of particles involved is what? Number of particles is very high. Okay, so n is all of the order of the Avogadro number, 6.023 into 10 raised to power 23 number. Now for simplicity I am just showing this. I am taking only two particles and showing these three energy levels. Okay, now what will happen for this? So there is a calculation. How will you find that? So you don't need that calculation so much. That is not so much needed. Calculation is nothing but this is the total number of microstates. Okay, this is the total number of microstates, and then from this this is the value. This is the value of the total number of microstates for Bose-Einstein. This is the value of total number of microstates for Fermi characteristics. Now from here you have to take the log of this. Okay, you have to take a log of this, and then if you do the differentiation of this and do it and take the first derivative of this and equate it to 0, then that will actually give you the most probable distribution, and from there you will arrive to the ultimate expression of most probable distribution. What is the expression? The expression is written like this: F E, okay, F E I is equal to Ni by Gi is equal to 1 by e to the power of alpha plus beta into Ei. Okay, this is for MB statistics. This is for MB statistics. This is for MB statistics, where alpha and beta are constants called as Lagrange multiplier. Lagrange's multiplier. Lagrange's multiplier. Okay. Alpha and beta are constants which are called as Lagrange's multiplier. Okay. Now so what is this Ni and Gi? You know that what is Ni, Gi? Ni is the number of particles, and Gi is the number of, I have already told here. What is Gi? I have already told here in the last class, that consider a system having energy levels E1, E2 and the number of particles in this level is say N1, N2, N3. Let G1, G2, G3 be the number of sublevels or the quantum states, okay, or the energy states or phase cell. Okay, Gi is the number of energy states in which these particles are to be filled. Okay, these are the number of these energy states in which this number of particles are to be filled. Okay, so the formula for most probable distribution function is this, is Ni by Gi. Okay, Ni by Gi is given as e to the power of alpha I plus beta Ei. So you are seeing that the Maxwell-Boltzmann distribution function is given like this. See, for velocity distribution also you will see that it is given like this only. Okay, that for this alpha for here is nothing but you can take this alpha for Maxwell-Boltzmann distribution as 0 only. Beta is actually 1 by kt. Okay, beta is given by 1 by kBt, where kb is the Boltzmann constant, T is the absolute temperature. Okay, so from here you will see the Maxwell distribution function also, like in here also you had done what to say, laser n1 by n2 is equal to e to the power of minus uh, e2 minus e1 by kt. Okay, you had done that, so it's just the same thing only. Okay, it's just the same thing. So this is FEI, this is a function of energy. Okay, means it basically what does this tell? It tells that the the probability that a particle, probability of a particle to occupy the energy state EI. Okay, it gives the basically the probability of a particle, probability of a particle to occupy, probability of a particle to occupy the energy state EI. Basically it's that, it's the probability it will occupy or it will not occupy. Okay, it gives the probability of a particle to occupy the energy state EI. That is actually the the this function, most most probable distribution function. Okay, and here this from here what do you mean Maxwell Boltzmann, this assuming Maxwell Boltzmann distribution function. This is very known to you, as I said, assuming Maxwell Boltzmann distribution function, the average speed. Okay, assuming Maxwell distribution, the average speed, then the root mean square speed. Okay, then most probable speed, okay, of the molecules of an ideal gas. So the molecules of an ideal gas can be calculated. Okay, can be calculated. Assuming the Maxwell Boltzmann function, the average speed, RMS speed, most probable speed of molecules of an ideal gas can be calculated. Okay, now comes your this is MB statistics. Now comes what happens for this B statistics. B statistics. Okay. Achha, for B statistics, what happens? For B statistics, this FEI is equal to NI by GI is equal to 1 by okay, 1 by e to the power of this alpha plus beta into EI minus 1. Okay, 1 by alpha e to the power of alpha plus beta into EI minus 1. Now here alpha is given by minus mu beta. Okay, and beta, you know, beta is what? Beta is 1 by kbt. So this is what? Minus mu by kbt. So what will happen here? What will happen? So this will be FEI will be equal to NI by GI will be equal to 1 by e to the power of alpha. That is this will be EI minus mu by kbt minus 1. Okay, where EI minus mu by kbt minus 1, where this mu is called as the chemical potential. Mu is called as the chemical potential. Mu is called as the chemical potential. Okay, now chemical potential. What is chemical potential? You just there's a short thing I'm telling. It's not so important in your syllabus. Chemical potential is that thing uh, like it denotes the number actually. I mean for diffusion it is important. Like I mean, মানে what will determine that particles will diffuse from which body to which body. Okay, that is particles having a high concentration of atoms has got a higher chemical potential. Okay, so you will tell that the particles will diffuse from a body at higher chemical potential to a body at lower chemical potential. Okay, particles will diffuse or will undergo diffusion, will undergo diffusion from a body at higher chemical potential, okay, to a body at lower chemical potential, to a body at lower chemical potential. Okay, if you write that mu is chemical potential, that is also okay. No need to write this. This is not so important. Okay, so this is the thing. So for B statistics, the distribution function is this thing. Ni by gi is equal to 1 by e to the power of ei minus mu by kt minus 1. See here, for what is the difference here? This one factor is the difference basically. This one factor is becoming the difference. This is almost the same as in Maxwell-Boltzmann statistics. E to the power alpha plus beta ei. Here also basically it is alpha plus beta ei only, but with minus 1 is entering. Okay. Acha. Now comes the very important thing, that is Fermi-Dirac distribution function. Now Fermi-Dirac distribution function. Fermi-Dirac distribution function. What is this Fermi-Dirac distribution function? Fei is equal to Ni by Gi is equal to 1 by e to the power of alpha plus beta into Ei plus 1. This is the Fermi-Dirac distribution function. Here alpha is given as what? Here alpha is given as minus Ef by kBt and beta is 1 by kBt, where here Ef is called as the Fermi energy, where Ef is called as the Fermi energy. This is very, very, very important. Ef is called as the Fermi energy. Okay, Ef is called as the Fermi energy. Therefore, Fei is equal to Ni by Gi is equal to 1 by e to the power of, this will be what? Ei minus Ef by kBt plus 1. Okay, this is the Fermi-Dirac distribution function. Okay, what does this tell? This tells that what is the probability that the particle will occupy this energy state Ei. Okay, the same thing, that is the probability of a particle. This is the probability of a particle. Fei, this distribution function is basically, what is Fei? Fei is basically the probability. Fei is nothing but the probability. Always remember this is a distribution function, but since we are concerning the number of a huge number of particles, that is why the probability will follow. That's I gave the example of the marriage party. This probability of will follow a distribution. Okay, a distribution means it's not constant, na? It's not constant. There are I mean lakhs of particles, 10 raised to 23 number of particles. So all will not have the same energy. Okay, all will not have the same energy. 1,000 particles will have one energy, 5,000 particles will have another energy, 10,000 particles will have another energy. So it will follow a distribution function. So now what is it? This is the probability actually. So the probability of a particle to occupy the energy state EI. Okay, this is given as this one. You can also tell like this, that this is the Fermi function, that is this denotes the probability that a quantum state at energy EI is occupied with a fermion. Okay, is occupied with a fermion. Similarly here it denotes the probability that a quantum state at energy EI is occupied by a boson. Okay. So you can also tell is that the probability of a particle to occupy the same thing, probability of a particle to occupy the energy state EI. So probability that a quantum state at energy EI is occupied with a fermion. The same thing. Probability that a quantum state at energy EI is occupied by a boson for this one. Okay, and probability that a quantum state this is not a quantum state. Probability of a energy state is occupied by a boson. Energy state having energy EI is occupied by a boson. Okay, achha, so these are the three distribution functions. Okay, these are very very important distribution functions. So you have to remember this. Okay, you have to remember these. This, then here there is this one. This is for BE. Okay, this is for FD, and this one is for MB statistics. I have already written it here. This one is for MB statistics. Okay, you have to remember, and you have to give this thing you have to give while there is a, this is the most important point, while there is a comparative discussion between I mean MB, FD and B statistics. Okay, so this is the thing. So now now there is a case when all these FD and B statistics will be equal to the Maxwell-Boltzmann statistics. What is that? Okay, that let us see. So there will be a condition where this quantum statistic, that is FD and B, will become same as MB. What is that? So you see here what is the difference between this FD, B and MB. This plus minus 1 factor is the difference. For Fermi there is plus minus 1, for B there is minus 1, and for MB there is nothing. Okay, so when will this happen? Okay, when will this happen then? So when, very very easy, I mean if you can write it like this, then this FEI is actually what? FEI is equal to Ni by Gi is equal to 1 by e to the power of alpha plus beta into EI plus k. Okay, now k is equal to 0 for mb, k is equal to -1 for b, and k is equal to +1 for fd. Okay, k is equal to +1 for fd. So here so from here you can see, so when uh, very clearly you can see when e to the power alpha plus beta ei becomes much greater than 1. Okay, when e to the power of alpha plus beta I is much greater than 1, then this you can neglect, I mean you can neglect here. For fei will be equal to ni by gi will be equal to 1 by e to the power of alpha plus beta into ei. Okay, when e to the power alpha plus beta is much greater than 1, then you can always neglect +1 and -1. Now when will this happen? When will this happen? This will happen means I mean is much greater than 1 means what? E to the power alpha plus beta ei, this will be much greater than 1 means what? This will be very small, that is ni by gi will be very less than 1. Okay, and this also means that this will happen. When will this happen? So this will happen for very high temperature. This will happen for very high temperature. Okay, this will happen for very high temperature. So what is the meaning of ni by gi is equal to 1? What is the meaning of ni by gi? The ni is what? The number of particles, and gi is the number of states, right? Ni is the number of particles and gi is the number of states. So I mean this is basically the particle density. So in that marriage party thing, if you replace the number of people with now this number of atoms ni, and gi is the number of states, that is number of stalls. Okay, so gi I told here also that gi is the number of I mean you can tell the number of sublevels, that is quantum states, or the number of phase cell. Okay, so suppose these are the number of these are buckets, and now balls are to be kept here. Okay, so number of balls is n and number of buckets is actually gi. So ni by gi is much less than 1 means what? So gi is much greater than that of ni. So what the the particle density, this is ni by gi is basically nothing but the particle density. The particle density, ni by gi is the particle density. Okay, ni by gi is particle density. So you can tell from this that at high temperature, temperature and low particle density, at high temperature and low particle density, the quantum statistics, high temperature and low particle density, the quantum statistics tend towards the classical one. Okay, at high temperature and low particle density, the quantum statistics tend towards the classical one. Okay, so if your question comes, generally it doesn't come for very big marks, that what is the condition for this thing to become classical statistics. We will say that at high temperature and low particle density. Okay, ni is the number of particles and gi is the number of states. Like here also, the unit cell or the phase space. So here the number of phase cells. Okay, number of phase cells is very high, but number of particles is very low. So what will happen? The particle density will be very less, and particle density will be very. Now this happens for what? This happens for the example of this happens is for rarefied gases. So rarefied gases. Okay, rarefied gases, the particle density is very low, and they are also definitely gases. They do not obey quantum statistics. Okay, in rarefied gases, definitely the distance between the gas molecules are very large. Okay, so this is the condition. Achha, another thing I forgot to mention, you have to add this point here. First of all, there you will add this point also, this three distribution function, and also you have to add here, see, only in Bose-Einstein I had added particle total energy and total number of particles of the entire system is constant. This will be added in all the this is for all the statistics, that is total energy and total number of particles. Total energy and total number of particles is constant. Okay, for the entire system, this is for Fermi dirac. Similarly for Maxwell-Boltzmann also. So in Maxwell-Boltzmann also the same thing, that is total energy and total number of particles of the entire system is constant. Okay, total energy and total number of particles of the entire system is constant. Of the entire system is constant. Okay, so add this thing. Okay, so in this class up till this much, in the next class again I will. So now these are very interesting things and all conceptual things. You must be able to conceptualize all these things. Okay, Fermi Dirac distribution. I will now go more deep into this Fermi Dirac distribution thing. Okay, so in next class I will continue with the Fermi Dirac distribution and what is Fermi energy and Fermi level, all these things. Thank you.